So I think I can start. So hello, everyone. Welcome to the fourth session of the SLT SIG. So my name is Marco Turchi, and I'm the secretary of the SIG. And here with us, we have also Professor Satoshi Nakamura, who is the president of the SIG. And the idea of these SLT SIG seminars is to allow people to present their work to a broader audience. So we are always looking for interesting topics, and we hope that among you there are the next speaker for the next seminars. Today we have Xavier. He is Xavier Iranzo. Sorry, I don't know if I pronounce it correctly. He's a PhD student at the University of Valencia, and also is working at Apptek. And today he's talking about his recent work on streaming translation, which is an important and relevant topic for the spoken language translation community. So I stop sharing my screen and I leave you the floor, Xavier. Xavier has told me that he preferred to have a question at the end, unless there are something critical that don't allow you to go ahead with his presentation. So yeah, the floor is yours. Thanks a lot for being here today.
Okay, I think it's sharing now, right?
Yeah, you can see everything. Okay. Thanks a lot.
Perfect. Thank you, Marco. And I also want to thank the rest of the organizers for inviting me. I also want to thank you, the attendees, for showing up for today. So today's topic will be about, as we said, streaming speech translation, and I'll be presented some work carried out jointly at Universitat Politècnica de València. So we will begin by talking about what is the task of streaming speech translation. Then we will briefly discuss the starting point, which is simultaneous machine translation. And then we will devote the rest of our time to specific evaluation for streaming machine translation, and then some specific models for streaming MT. So first of all, to introduce what is the task that we are interested in. We are interested in streaming speech translation, and we define this as the task of providing translation, but for an unbounded input audio stream. So in this case, we are not interested in just translating short utterances, but rather longer audio input. So for example, a TED talk, which is, let's say, 15 minutes, or a university lecture, which might be 1 or 2 hours long. Then, of course, we want to provide this translation under some constraints. We want to provide translation in real time. We want to be able to show the user the translation in real time. And then this means that we only have a limited context, right, to perform the recognition. So we have these latency constraints that are going to affect our solution. And then because we are interested in the in the task of providing translation for long audio streams, we would also wish to have a realistic way of evaluating this. So we want to move towards stream level evaluation. So just to give you a quick recap of what we do at UPV, we use a cascade system approach for speech translation, but everything I'm going to talk about in this seminar can directly be applied to an end-to-end system. So hopefully this will provide you some useful insights. So first of all, we have a streaming ASR system, and this is a hybrid system which uses a chunk-based LSTM for the acoustic model and then a transformer language model. This is followed by a recurrent segmenter, and this is basically a classifier that receives the output of the ASR system, and then for every word it decides if it's going to insert an end of sentence, so a line break, and then the output of this segmenter, so some sort of sentence like unit, is what is provided to the MT system. And then the focus of this seminar will be on the MT part. We will first look at evaluation, because if we don't know how to evaluate, then it's going to be hard to provide some insights. And then we will specifically look into streaming specific models. So we will then start our path by looking at the baseline, that is at a sentence level, simultaneous translation. And this is the task of translating a sentence before it is fully available. So we are doing translation for partial prefixes. Here you have the classic decision rule for machine translation, but in this case, because we are on the simultaneous case, you can see that we have a restriction on the source sentence. So we don't have the whole sentence available. Instead, at each time step, that is every time we are going to write a new output word, we are only going to have a prefix available. And this is given to us by what we call the delay function, G of I, which tells us the amount, so how many source words are available for writing the if output word. Now, what this means is that when we have a simultaneous model, let's say its behavior, or this model can basically be defined by this function, by this policy function G of I. So at each time step, the policy basically has to decide between two things. It can either read an input word, that is, it can wait for more context, or just write an output word. And then in simultaneous MT, it's quite typical to have a baseline policy, which we call wait K, which is quite a simple policy. It first waits for the first K words to arrive, and then you alternate between writing and reading. So here you have the equation which defines this behavior. And then on the denominator, you have this gamma parameter, this length ratio, which is the ratio between the target and source sentence lengths. Ideally, we would wish to have access to this, but because we cannot know beforehand how long our translation is going to be, then our model is going to, let's say, try to guess as best as possible this value. So here I'm showing you in graphical form the trellis or the log of the translation of a wait one system. Then when you move one square to the right, it means you are reading, you are receiving a new source word. And when you move one square downwards, you are writing, you are producing one output word. So now that we have looked at the systems, let's quickly look at the evaluation metrics. So we typically compute latency at the sentence level, and then there are many latency metrics, but most of them can be, let's say, understood in this framework. So you do a sum over a cast function, which is defined for each target position I. And let's say this means that every time you produce a new output word, you are going to have some cost. You have incurred some cost. And then you have in the denominator, you have a normalization function, which typically acts over all target positions. So most latency metrics can be understood as somehow providing a normalized cost over all the words that your system produces. Now, this is done on the sentence level. If you want to, let's say, get one score for your evaluation set, you typically just average the latencies across all sentence pairs. So take notice that here we are evaluating all the sentences in isolation. There is no interaction between them. We'll later get back to this. So here I've quickly shown the three most popular metrics, AP, AL, and DAL. We are now going to look into detail into them, so you don't have to quickly take notes of this. But see that the cost function always depends on the delay function G of I, and then, as I said, for the normalization function, you always take into account the length of the output that you have produced. So you produce some sort of average score overall target words. So let's look at the first metric, average proportion. This is a very easy to understand metric. So you're just going to sum all the cost functions. So you are going to sum the cost associated to each target word, and this cost is just the amount of words that you have that you need to wait in order to produce them. And then you just divide by the area given by this square. So this is quite easy. You just sum the different rows, and then you divide by the area, and you get a score, which can more or less be interpreted as which is the proportion of the source sentence that your system required in order to produce the output. So in this case, 0.56, then more or less always your system required, like, let's say, half the input sentence. This is not exact interpretation, but it's a way that you can think about this. Then we can do, let's say, some refinements over this, and we have the average lagging metric. So in this case, we have, as previously, we have the delay function. We have G of I, which it's representing the policy of the model that is being evaluated. And then we are going to compute the difference between our model and a special model, which is shown here in blue, which is a weight zero oracle. So this is one model that it starts producing output without needing to receive any input words. So it's, let's say, the best possible translation, the best possible translate of the oracle. So you basically compute the difference between these two latencies. Sorry, between these two policies, and then that is your average lagging. So in a way, you can interpret average lagging as the difference between your actual model, so the behavior of your model, and the weight zero oracle. So how many words you are lagging behind the oracle. And you only compute this measure up to the point that the whole source sentence has been read. Here you can see it graphically. So we are here showing the policy of a weight 4 system, and then we are just computing the difference between our system, shown in red, and the oracle system, which is shown in blue. And then on the right here you have the value, which is 4. So it makes sense. We have a weight 4 model, and then this is always lagging behind 4 words behind the oracle. And last but not least, you have a differentiable average lagging, which is like average lagging, but the write operations are not free. That is, every time you are going to produce a write operation, you are going to incur in some additional cost, which is the inverse of the length ratio, so 1 over gamma. Then if you do this modification, you compute it for all target positions, and here you can see the result. So in this case, a weight 4 model also gives you a DAL of 4. Once again, it lacks 4 words behind the speaker. Now, now that we have seen all the current setup for evaluation of streaming simultaneous MT. I want to ask you this question. So do you think that what we have seen makes sense? So are the current practices for simultaneous MT evaluations realistic? Is this so are we evaluating what we are actually hoping to achieve? So I want to highlight some problematic aspects. So first of all, as we have said, we are evaluating sentences on isolation. So this means that even if I take a long time for translating one sentence, this is magically fixed when I end the translation of this sentence. Of course, this doesn't make sense if you consider the case that, okay, if I take a lot of time in order to produce the translation for one sentence, this of course is going to have some effect on the following sentences. I cannot show to the user a lot of subtitles at the same time, right? So then ideally we should take this somehow into account, that sentences are not isolated in the void, but that we are translating the part of something bigger. We are translating a very big video or audio stream. Then also there is the issue of segmentation. So if we compute this latency matrix, we are, let's say, constrained or restricted to using the same segmentation across all systems to compare them. Maybe this is not a good solution if we somehow come up with a better segmenter. And also what happens if, for example, we have a segmentation-free model that can just process an stream and doesn't care about any explicit representation of segments. And last but not least, currently, most of these systems are evaluated with short segments. So, for example, one of the most popular speech translation corpus, must-see, has on average segments of 4 or 5 seconds long. So then, in this case, are we, let's say, providing a realistic evaluation condition? So, I mean, if our audio is just 4 seconds long, is it really necessary to provide simultaneous translation? Maybe just waiting 4 seconds is fine, and we provide the answer with an offline model. So if our goal is to translate a very long audio stream, but then we evaluate on sentences or segments which are 4 seconds long, then maybe this is not very realistic. So to sum up, I want to highlight the fact that maybe we are interested in doing one thing, but we are actually evaluating for a much simpler or a much easier condition. Therefore, it would be ideal to carry out the evaluation, but for the whole stream. So how can we do this? There have been already some proposals to do this. So, for example, there is the concat1 approach, where you basically say, okay, I'm just going to concatenate together all the sentences. I'm going to produce a translation for this very long sentence, and then I'm just going to evaluate it with the standard latency metrics. But however, this introduces a very big assumption, which is that based on the way the metrics have been defined, this means that the Oracle system is going to have a constant writing rate across the entire stream. And actually, when you compute the statistics for any standard evaluation set, you will find that this is not true. There are huge differences in target to source length ratio across the different sentences. So perhaps this is too strong of an assumption. So I'm going to just show you a quick toy example. We are going to translate 2 sentences. So the first sentence has 2 words in the input, and the output is also consists of 2 words. So our length ratio is 1. And then we are also going to produce the translation for a second sentence, which has 2 words in the input and 4 words in the output. So we're going to do this with a weight 1 system. So I have provided you here the logs of the different delays. And then once we have produced the translation with this weight 1 system, then we're going to evaluate under 2 scenarios. We are going to compute the standard sentence level metric, so each sentence on isolation. And then we will compute using this concat1 approach, where we just join the 2 sentences when computing the lattices. And our expectation is that if everything works properly, AL and DAL should be 1 or really close to 1. However, it turns out that this is not the case even for this toy example. So here you have the whole computation, but I just want you to focus on the first and last columns. So on the upper part, you have the results for the individual sentences when we evaluate them in isolation. And this more or less makes sense. So AL is 0.9 and DAL is 1.0. Okay, everything's working perfectly. But then for the concat1 approach, then as you can see, AL is 1.2 and DAL is 1.5. So this is higher than we expected. Now this is just for a toy example, but when we actually compute this for standard evaluation sets, then what we find is that first of all, average proportion, so AP is always going to give you 0.5. If you think about it, this makes sense because the difference between any reasonable system and the weight 0 oracle is very small when you divide by the area of the square. So the area of the square is very big because you have a long source input and a long target output. Then when you do this division, then you are just left with 0.5 always. So there is no way to distinguish between the behaviors of any system. So then AP is not really useful in this case. And then for AL and DIL, there is a very big issue, which is that the values that you obtain do not reflect the real behavior of the model. And this is because we are constrained to using a single writing rate for the oracle, but then this means that at some point the speed is going to be underestimated and at some points it's going to be overestimated. And if in fact, because DAL always has this cost associated with the write operation, then this means that the value of DAL is always going to grow bigger and bigger. So as an example, if we first carry out translation with weight 1 to 5, and then we do this concat1 approach and compute the results, you can see, for example, the AL results, and okay, you will see that this is not very interpretable. So first of all, you have negative latencies, which we are not even sure what it means. But in fact, if you look at it, the ranking, that is the order between the systems, has been altered. So if you just looked at the results without knowing the models, you would think that the behavior, for example, of the weight 3 model is very different than the weight 1, or is faster than the weight 1, when in fact it is slower. I mean, the actual translation has been carried out with a weight 3 system, which is slower than a weight 1. So what we can conclude from this is that if we just use a single fixed writing rate for the oracle, then we cannot do streaming evaluation. So we proposed this idea that maybe it would be possible to do this evaluation if we have, instead of just one single writing speed for the oracle, we have access to some sort of local representation. So for every sentence-like unit, we are going to have access to some local writing rate for the oracle. Then what we are going to do is, okay, we are going to keep track of the latency using just a global delay. So this will be like in concat1. So we are going to take into account the interactions between the different sentences. But we will take this global representation. We are going to modify it to convert it to a local representation and then compare it against the local oracle. So if we can somehow obtain good local representations for the delay and for the oracle, then, okay, we are ready to compute latencies. So how can we do this? We are just going to introduce a very simple modification to the way we define the latency metrics. So instead of just looking at a local or isolated delay, G of I, we're going to look at a local representation of the global delay. So first, we want to know, okay, what is the global index? So the index with respect to all the words in the stream for a given word of a given sentence. Then this is very simple to compute. You just do this. You add the length of the previous output, and then you get the global index. So then you take this representation, the global delay, you subtract the length of all the previous input sentences, and then this gives you a local delay, which can be interpreted as how many words of the current sentence I have needed to wait. So how many wait operations I have done when computed locally. So with respect to this local sentence. If we are able to, let's say, if this transformation works, then we can just compute the metrics straight away. Now we need to obtain a good sentence level alignment for this, in order to produce the evaluation. And as we said, this is needed for computing the local latency representation for the local oracle, and then just for averaging the matrix. So it turns out that there is a straightforward way to do this. We can employ the same trick than we do for quality evaluation. And then we can just realign the sentences. So we can realign our hypothesis with the reference translation. And you can, for example, do this with a minimum edit distance. Then this way, after the realignment process, even if our input and our output is just one single stream in the source and one single stream in the output, so just one single very long sentence in the input and one single very long sentence in the output. After we perform the realignment, then we are going to obtain sentence pairs, and then we can take the sentence pairs, we compute the local representation, as I showed you on the previous slide, and then we just do the standard latency computation. So using these tricks, we are actually able to perform streaming evaluation. And we are now just going to see if all the assumptions that we have done actually work, because As I said, so we are using some automatic procedure for doing the realignment. Then maybe this is going to have some effect. So we are going to compare the results of just using a real system, which has the recurrent segmenter and a weight K system, and also 3 oracles. So they are going to use the reference segmentation at the input instead of our recurrent segmenter. We can also see what happens if we do if we use the reference resegmentation instead of using this automatic procedure. And also we're also going to let's say provide some hint to the model and give it the appropriate writing rate for each sentence. And to recap, what happens if you had tried to do this using concat1, then you will have obtained some very strange values, which first of all, they cannot be interpretable. So, I mean, so the actual system is 1, 2, 3, 4, or 5 words behind the speaker, but these numbers are telling you a different story, which is not true. But then also, so the ranking between the different systems will have been altered. However, if you apply this proposal for streaming evaluation, then you can finally obtain some results which are good. These results give you the correct ranking, so they correctly rank the systems from lowest to highest latency, and they are also interpretable. So they provide you a much clearer view of what your system is actually doing. So a weight 5 system has a average lagging value of between 4 and 5. This means that the weight 5 system is 5 words behind the speaker. This is what we actually wanted. There is a small difference between the real system and the results computed for the oracles. And this is because, of course, the real system doesn't have access to the correct writing rate. So in this case, it is more aggressive, but this is not an issue of the actual computation of the latencies. This is the real behavior of the model. So now that we have seen how to evaluate latencies for the streaming case, then let's dive deeper into how we can construct better models for streaming machine translation. So we are interested, of course, in real-time translation, but we must be able to provide this translation for an unbounded input stream, which might be very long. Then the task is to translate a very long stream into a very long translation. So we have rewritten the standard decision rule for machine translation, but in order to compute it for this streaming scenario where we have capital Y, which is our target output, and capital X, which is our input. And then the amount of words that are available will be given by capital G. So this is going to be our delay function for the streaming case. Now, of course, if you had to take the whole stream into account at every time step, this will be very complex. So for efficiency reasons, we are going to introduce a history function, h of I. Then in this case, this means that the translation is actually going to be carried out by using a sliding window, which is defined by g of I and h of I. And even if our goal is to translate these long streams at training time, we do have some access to additional information. In this case, we can access the segmentation information, which has been already It's already present in the training corpora. And we could, for example, store this information into two equal length vectors, A and B. So using these two vectors, for example, it is quite straightforward to compute a modification to the standard simultaneous weight K policy in order to produce a policy which has the same behavior than the weight K policy, but it can be, let's say, its behavior is defined at the stream level. So we have this, then this means that we can have a weight K system for the streaming scenario. And now let us look at the models. So during all this time, we have been using standard transformer, encoder, decoder, sequence-to-sequence models. When looking at the, let's say, at the encoder side of things, so typically in standard machine translation, we use bidirectional encoders. So when computing the self-attention in the encoder, we basically have access to everything, right? So here we have an example of the translation process of a weight 4 system. So on the upper part, you have the timestamp at which you produce the first output word. So it's a weight 4 system. Then this means that G of 1 is equal to 4. Then on the lower part, you have the time step where you produce the second target word. So G of 2 is equal to 5. Then in this case, this bidirectional encoder has access to everything, right? But it turns out that if you just take this encoder and put it into the streaming scenario, this does not work so well. There is quite a strong performance degradation. So this is why it is typically used instead the unidirectional encoder. So in this case, in the encoder self-attention, when you are, for example, producing the encoding for the third input word, you only can access that word. So you can only access the current word and all the previous words. And even if you receive more, more context, then you are not going to be allowed to use it. This in practice performs better than the bidirectional encoder, but in this case, as you can see, there is a lot of information which is available, but it's not being used. So as a way to bridge the gap between these two encoders, we have proposed what we call the partial bidirectional encoder, or PBE, which in this case has access to more positions. So in this case, we are going to allow it to attend up to position number K. So it is not fully bidirectional, but it has access to more information. And under this current formulation, it gives a very interesting property, which is that at training time, you can compute all the intermediate steps that you need for computing the gradient in just one forward pass. So this is quite efficient during training. You don't have any additional slowdown. And in principle, the encoder has been provided more information, so maybe it can take advantage of that. Then, now that we have seen the encoder side of things, let's look at how we can actually build these streaming systems. So for this work, we have opted for building streaming samples using a concatenation approach. So here, if we have some document, for example, here we have a document with 3 sentences. The first sample is just the first input and outputs sentences. But then on the second sample, we have the second sentence, and we have also provided as additional context the first first sentence. And this is what we call streaming history. So for each sample, we are going to have a history window, a window into the past. This window is going to have some predefined maximum size or maximum length. And then as long as this size is not exceeded, we are going to provide the previous sentences and context. And in this case, we keep the constraint that we only keep a sentence in the history window if the maximum size is not exceeded. So we will never have a partial prefix in the streaming history window, only full sentences. In this case, this is a toy example with a maximum history size of 5. And this is why for the third sample, we only have the second sentence in the history window. If we had included the first sentence, the maximum size would have been exceeded. Let's look now at some results. So we are going to do the experiments on the IWSLT 2020 English to German data. And then we will evaluate on the German-English direction and also on the English-German. All the models have been fine-tuned on the must-see corpus, and we are just using the standard transformer big model. Now for the weight K policy, we employ the multipath approach. So during training, we don't have a fixed value for K. We sample a different value at each batch. And then this means that at inference time, we can provide a fixed value for K. And using this, we can control the latency of our system. So let's first look at the effects of streaming history. So in this case, we are going to test different values for the maximum size of the streaming window. On the x-axis, you have the value for the K of the weight K policy. And then on the y-axis, you have the BLE, the quality, on this IWSLT 2010 dev set. So as you can see, you have the, let's say, the baseline, so the sentence level system with age equal to 0, and then we try adding a history window in steps of 20. And then you can see how, in this case, it turns out that having access to this context, to this streaming history, it's quite helpful to the model. You have very significant improvements. And in this case, let's say the optimal value is a history size of 60. So higher values do not provide any additional improvements. In terms of the encoder, so let's compare the unidirectional with the PBE encoder. In this case, at low latencies, they behave basically the same. But then at higher latencies, so as the PBE model has access to more information, then it turns out that it performs slightly better than the unidirectional model. And then let's compare our streaming approach, where we just take we take the recurrent segmenter and our streaming model and compare it with an already existing streaming approach, which is called ACT. And here I'm showing you the results, the quality, the BLE results, and also the latency metrics computed for the streaming case. As you can see, in this case, our system is almost able to achieve the same level of performance, but it's actually much faster. So it achieves this with a fraction of the latency. And this, if you do an analysis, one of the reasons for this is that the adaptive policy, so ACT is an adaptive policy, it falls behind the speaker at some point, and then it doesn't recover. That is, it doesn't have any sort of catch-up mechanism. But instead, because we have combined a weight K and a segmenter model, this ensures that the model always keeps up with the speaker. Because every time we detect an end of sentence event, every time we detect a line break, then we translate everything that we have up to that point. And then that way, every time we have an end of sentence, we synchronize with the speaker. That is why we never fall, we are never far behind the speaker, even if this is a long test set of, I think, something like 6 hours of audio. So during all this, we are never very far from the speaker. So this is quite good. And we have also compared ourselves with the participants, so with the 3 submissions to the IWSLT 2020 simultaneous translation task. At the time, those 3 submissions were sentence-based submissions. So then we compare them against our work, which has access to this streaming information, has access to this context. And then you can see how across all the latency regimes, having access to this streaming information is actually quite helpful for this. And this is a realistic scenario because you are doing translation for long videos, so you already have access to this contextual information. You just need to take advantage of it. So to sum up and to conclude, I hope that I was able to convince you of the need for realistic simultaneous MT evaluation. I have shown some techniques which can help you carry out evaluation for the streaming scenario. And we have also shown how having a streaming MT system that has access to this contextual information results in significant quality gains. And once again, I want to highlight that if you are doing translation for very long audio streams, you already have access to this information. You are just not taking advantage of it. So I encourage you to look further into this scenario of streaming speech translation. And with that, I'm going to conclude the talk. Thank you all for your attention, and hopefully there are some questions which I will be very happy to answer. Thank you, everyone.
Thanks a lot, Sevi, for the very nice talk and really complete. You start from the evaluation to the system. So I really like your talk. So any question for Xavier? There is Volker. Oh,
I was actually only clapping my hand.
Sorry, I looked there, raised the hand. Okay, sorry. I have some questions. So if no one, I will be the one breaking the ice. So I was wondering, I'm really interested in the idea of adding context, okay? So I was wondering, because I wasn't able to understand from your plot, how adding context impact on latency.
Okay, so it does. I mean, I have actually run the numbers, and they are on the ACL paper. So even if you add, let's say, a history size of 60, so 60 words to the source sentence, if you run it on a GPU, the system is fast enough that there is no slowdown. That is, of course, it is slower than the sentence based system, but it is faster than the human speaking rate. So there is no slowdown.
Okay, so you mean that if you have a context of 60, you don't see any additional latency. That's interesting to me.
So, I mean, I'm talking about latency at the, let's say, computational level, right?
So the computational aware,
yes,
not
yes.
the, okay, the theoretical
yes.
one, okay. So that you rise also, you touch another topic that for me is interesting. When you present the results at the end, or when you compare with the other system on the audio facility data, did you use the computational aware or the computational unaware?
No,
Here.
this is non-computational aware.
Okay. Okay.
And I mean, I just took the logs from the task, and I compared our system with them. This was done after the fact, so we didn't participate in IWSLT 2020. This is just our system compared with the three submissions to IWSLT.
I see. Here I have another question. You see that you have a big gap, big advantage in terms of performance compared to the other system. Do you have an idea what is the main source of gain? Is the context information that you add at the beginning, or the encoder? Because I mean, the gap are important, 3-4 blue score on most of the systems.
I think it's mostly due to the context. So the on-track submission is also using this multipath strategy. So the models are really similar, except with the difference in the encoder that I mentioned. In fact, they are using just one single system. We are using just one single system. The latency is adjusted at inference time. And then I think there is from doing this is just let's say a very quick analysis of just looking at the sentences. My intuition is that because this is must-see and the segments are not very long, as I said, they are maybe 4 or 5 seconds, then even if there is a strong locality, you have a very big advantage if you have access to the previous or to the 2 previous sentences and so on, because the segments are very long. So then you have very short. So then that is why it can be quite helpful to have access to this streaming context. And then maybe there were some, let's say, other data preparation techniques and so on, but I think most of the gains is due to this contextual information. Okay,
which look very interesting to me. And any other questions from the audience? Satoshi?
Yes. Thank you very much. So can you hear me?
Yes.
Yes. Thank you very much for your presentation. I'm very impressed. So let me confirm first thing is that so including the history. So this means that you keep the history information and put into the partial bidirectional LSTM.
No, so for the MT system, this is just a transformer encoder decoder. I assume you're talking about the MT component. Is that correct?
So I'm asking the page 33, his streaming window.
So for the streaming window for the empty side, right?
Yeah, right.
Yeah, so for all the, let's say, for all the 3 encoders that I have shown, apart from, let's say, the only difference between the encoders is just how you restrict the self-attention. But what the encoder actually sees is this type of samples. So we always provide this streaming window. Here I have shown the streaming window in light gray. I don't know if it shows very clearly, but it's on a different, at least on my screen, it's on a different color.
Yeah, thick one is was in a streaming window. Okay, so then so in a history, you use the 0, 10. I forgot the number, but those number was in a history window and then put into.
Yeah, so we tested different sizes. I mean, we used a step size of 20.
Mm.
So basically, we just keep. So we keep all the last sentences, and then during inference time, when we finish the translation of a sentence, we add it to this window. And then we remove the oldest sentences until this maximum size is not exceeded. So the oldest sentences are the ones which are eliminated or forgotten. They are the ones that are forgotten first, and we always keep the more recent sentences.
Yeah, like a sliding window. Okay, thank you very much. I understand. So, and I think I agree that IWSLT needs to evaluate streaming ST, and so why don't you propose the new evaluation scheme for next year IWSLT?
There were some discussions, I think, already at IWSLT, or at least it was mentioned on the streaming. Sorry, on the system, on the paper about the evaluation campaign. But yes, I will be. I'm open to coordinating, or let's say helping in any way that I can, in order to maybe introduce this streaming component for IWSLT. Yes, I think it would be quite interesting. Thank you.
Great. Yeah, thank you very much.
I think there was a kind of discussion during the presentation of the simultaneous task or after that. So I think, yeah, please get in contact with Juan and the other organizer. So Volker, I think now you raise your hand. It's the correct.
Yeah.
Thanks.
After the little shock. So thank you very much for your presentation first. And so I have a question, and if you answered it already, my apologies. I had to take a call in the middle of this presentation. So it seems to be say interesting to follow some probabilistic modeling. You know, you have a probabilistic modeling, like when is a sentence finished. In speech recognition, you have something like you have a certain reliability of what you hypothesize as output or so. Is there anything you have envisaged or tried where you used to compute something like a reliability of this is a chunk of words that now can be translated, and now this is the next word that you better use to wait? Is there anything like that?
Yeah, so the let's say the current segmentation model that I'm using, it's let's say it's quite simple at the moment. So here I'm just taking a hard decision based on the class which has the higher likelihood. And so basically, if the likelihood is high for the split class is higher than 0.5, then I take a split decision. But indeed, in principle, it should be possible to let's do some more, let's say, a more fine-grained behavior, right? Or somehow take the output probabilities of the segmenter into account, instead of just a hard decision, which is what I'm currently doing. Indeed, I think it will be more helpful. For example, if the segmenter is not strongly confident on this end of sentence decision, maybe we can wait for more context before committing to a decision. Okay. I agree.
So it's basically in your pipeline, but of course you started with this research because you first have to get a feel. I think that's the way to start, of course. Yeah. Okay. Thank you.
I have a probably similar question. Are there any other questions? So about your segment, when you show the source and the target segmentation, how you concatenate the context, can you go to the slide number 32? I don't remember now what slide it is.
So for the samples, for the streaming
here.
samples, yes.
Yeah.
Yes.
Here, when you have the target, for the word training the data. How does it work? I mean, when you have a language of different word order, I mean, you have German on one side, English on the other. Because here, it, for me, makes a lot of sense when the two languages as VO. But when you have different word order, how does the system, I mean, add a lot of noisy?
So I only tested this for German. So for German English, English Spanish, and French English, I think. So I have only done experiments on these language pairs. I haven't tried it, for example, with English Japanese. I'm not, let's say, I'm not sure what effects it's going to have. I know that there is, let's say, a strong difference in performance. So maybe what works for English, German, simultaneous translation is not the same as for other languages. This is something to definitely look into the future. The way I try to, let's say, avoid these problems as much as possible is by the constraint that only complete sentences, so only whole sentences can be into the history window. So if the length is going to be exceeded, I'm not going to cut it in half. I throw away the whole sentence. And this way, I always ensure that there is a consistency between the source and the target. Otherwise, there are problems. If you don't have this constraint, I have tried it. I have some external, some internal results, and indeed, there are a lot of problems. You end up with misaligned histories and so on. It's not so good.
I see. Okay, thanks a lot. So we are already out of time. So do you have any other questions for Xavier? No one. So thanks a lot, Xavier, for taking part in the meeting and presenting your work. Really very nice presentation, and thanks a lot everyone for attending. So we are recording the presentation, so will be, I'm doing myself without leads, so I hope I'm able to put it online on the AWSLT website. So the just last announcement is that ideally we would like to have a break during the summer with the seminars. So for sure we have a seminar in September about sign language and sign language translation, but we are discussing internally to see if we can have also some other presentation seminar during the July and August. In case I will update you on the main list. So thanks a lot, everyone. And if we don't see in July and August, have a nice summer, and we will be back on September with another seminar. Thank you, everyone.
Thank you. See you. Bye.
Bye-bye.
Thank you. Bye.